Hey everyone, welcome to this explainer. Have you ever turned on your tap, filled up a glass of water, and just marveled at how perfectly crystal clear it is? I mean, it's something most of us completely take for granted every single day. But that clarity, it's not just some aesthetic luxury. It is the hard-won result of an invisible, microscopic battle against something called turbidity. Today, we're going to track the really fascinating journey of water, from a muddy natural stream all the way to that pristine, highly regulated glass in your kitchen sink. Okay, let's dive into this. Take a quick look at the stark contrast in these two environments. On the left side, you've got a fish swimming in this murky, cloudy water, right? And on the right, two fish in perfectly clear water. Before we even get into the heavy science of what makes the water on the left look like muddy tea, you can immediately see the visual stakes of what we're talking about. I mean, if you're that fish on the left, your entire world is altered. Your visibility is totally shot, the water feels physically different, and survival just got a whole lot harder. This cloudiness you're seeing, that is the physical manifestation of turbidity. All right, here's our roadmap for today. First, what is turbidity? Then we'll look at its origins, the ecosystem impact, and our removal methods. After that, we'll cover safe drinking limits. And finally, the really surprising hidden dangers of the shield effect.
Let's start with Section 1. What is turbidity? Defining water clarity. What is it that actually makes water look so cloudy?
Simply put, turbidity is a measure of water clarity, or, its cloudiness. But the actual science behind it is purely optical. It's caused by suspended particles hanging out in the water, things like clay, silt, really finely divided organic matter, and microscopic organisms. When a beam of light hits all these suspended particles, that light is scattered in all directions, instead of passing straight through. Because of this massive scattering effect, the radiant power of the light beam that actually reaches a detector is significantly reduced, which is what gives the whole mixture that cloudy appearance. And we actually measure this optical property using a specialized technique called nephelometry. And this brilliantly illustrates what that looks like out in the field. You can visually perceive just how dense high turbidity can be. This researcher's water sample is so incredibly packed with particles that sunlight can hardly penetrate it without scattering completely. This right here is what high turbidity looks like in the real world, way before any human engineering gets involved to clean it up.
Moving on to Section 2, Origins, looking at the natural and human causes. Where do all these light-scattering particles actually come from in the first place?
Well, the origins of turbidity are basically split into natural factors and human-induced activities. On the natural side of things, you have heavy spring snowmelt and precipitation that really churns up our rivers. You've also got microscopic algae and plankton that just naturally float in the water column. But let's be honest, humans play a massive role here too. Urban construction, runoff flowing off impervious city streets, untreated wastewater discharges, and agricultural fertilizer runoff, which, by the way, fuels massive algal blooms. All of these dump incredible amounts of suspended solids right into our water systems.
For instance, check out a collapsed stream bank. This is a prime example of human-induced changes. When we alter the surrounding landscape, like with upstream land development, farming, or forestry, it actually weakens the natural hold of the soil. The result? The bank literally just collapses, dumping all that loose soil, clay, and silt directly into the source water supply.
Which brings us to Section 3, Ecosystem Impact. The severe threats to aquatic life. Let's examine what happens when these suspended solids completely take over an aquatic ecosystem.
When turbidity levels get out of control, it triggers this devastating cascade of failures out in the wild. First off, these physical particles can literally clog the gills of fish and the filter feeding systems of other aquatic animals. It effectively suffocates them. It also severely hinders visibility, which makes it nearly impossible for predators to hunt. And because all those particles are scattering the light, they stop sunlight from reaching submerged aquatic plants, shutting down photosynthesis and drastically reducing the water's dissolved oxygen. Oh, and it gets worse. These darker suspended particles actually absorb heat from the sun, physically warming up the water. And perhaps the most alarming part, these particles act like microscopic transport vehicles. They absorb toxic metals, nutrients, and organic pollutants, dragging all of that nasty stuff down to the bottom sediment where it poisons the whole ecosystem.
All right, Section 4, Removal Methods. Let's trace the water treatment journey. If we are pulling our drinking water from these turbid, potentially polluted sources, how in the world do we get it out?
Let's move to and see how this builds into the massive engineering solutions we rely on every day. When raw water enters a treatment plant, it goes through a highly controlled, systematic journey. First up is pre-settling. The water is held perfectly still so the heaviest, largest particles can just sink to the bottom naturally by gravity. Next is coagulation and flocculation. This is super cool.
Chemical mixers are added to make all those tiny, stubborn floating particles stick together into heavier clumps, which we call floc. Those heavy clumps then settle out. Finally, the water passes through filtration systems to physically catch whatever tiny bits are left.
And we've made an incredible technological leap in that final filtration step. Now, older, basic methods like slow sand filtration, they work by letting water slowly trickle down through a bed of sand and biological layers. And hey, it's effective for basic turbidity removal. But today, we often use highly advanced membrane filtration, like microfiltration or ultrafiltration. These membranes force the water through microscopic pores that are so unbelievably small they can physically strain out viruses and bacteria. They can achieve up to a 7-log reduction of microscopic threats. In plain English, that means they remove upwards of 99.999999% of dangerous organisms like Cryptosporidium and Giardia. It's a real game changer.
Next up, Section 5, Safe Limits, the strict numerical rules behind our tap water. We've cleaned the water, right? But how do we scientifically prove it's safe to send to your home? Well, we use extremely strict numerical regulations.
Remember earlier when we talked about nephelometry? Well, turbidity is measured in Nephelometric Turbidity Units, or NTU. And the crucial number to remember for your visual clarity is 4. At 4 NTU, water becomes visibly cloudy. If you pour a glass of water at 4 NTU, your naked eye will perceive it as milky, muddy, or kind of dull. It completely loses that aesthetic appeal, and, naturally, consumers immediately begin to question if it's safe to drink.
But here's the thing. Our safety standards are vastly stricter than what the naked eye can ever see. While water is considered crystal clear at anything under 1.0 NTU, the EPA and the World Health Organization mandate that conventional filtration plants have to hit 0.3 NTU or less in 95% of all their monthly samples. And those high-tech membrane filters we just talked about, they consistently output water at less than 0.1 NTU. We are legally demanding clarity long before a human being could ever detect even a hint of cloudiness.
Which leads us to Section 6, the shield effect, the hidden dangers lurking in microscopic shadows. So the crucial point is, why are we so incredibly strict about this? It all comes down to the hidden dangers of what we cannot see.
Seriously, I want you to ask yourself, if the water looks perfectly crystal clear to the naked eye at 1 or 2 NTU, why do treatment plants spend literally millions of dollars and massive amounts of energy to force it down to 0.3 or 0.1 NTU? Why do we care so much if we can't even see the problem?
The answer is something called the shielding effect, and I'll tell you, this is the most critical health revelation of this entire explainer. Those microscopic particles of dirt, clay, and organic matter, they aren't just harmless little floaters. They act as physical hiding spots, literal microscopic armor for dangerous pathogens. Nasty, disease-causing microorganisms like Cryptosporidium and Giardia physically attach themselves to these particles. So, when the treatment plant hits the water with ultraviolet light or chlorine to disinfect it, the dirt particle physically blocks the UV rays or absorbs the chemical, completely shielding the pathogen inside. If that turbidity isn't removed first, the pathogens survive the disinfection process and make it straight to your tap.
And this creates a severe engineering consequence. If the turbidity in a plant rises above 1 NTU, it means there are simply too many shields floating around in the water. The treatment plant then has to pump in significantly higher doses of chlorine, or keep the water in contact with the disinfectants for a much longer time. In the industry, this is known as achieving adequate C, which is the product of the disinfectant concentration and the contact time. Keeping turbidity as close to absolute zero as possible is quite literally the best way to ensure our disinfectants can efficiently and safely kill the germs without having to over-chlorinate the whole water supply.
Okay, real quick, before we wrap up, I want to share a fun, surprising fact so you don't panic the next time you use your sink. Sometimes you might pour a glass of tap water and it looks totally milky white and cloudy, but watch it closely. If it clears from the bottom up, it's completely harmless. That isn't dangerous turbidity, it's just supersaturated air bubbles caused by the pressure in your pipes being released. True turbidity from suspended solids won't magically clear itself up in a few seconds like that.
Which leaves us with this. The water we drink really is an absolute marvel of human engineering. It's constantly monitored and aggressively filtered to protect us from invisible threats hiding behind microscopic shields. So the next time you pour a crystal clear glass of tap water, will you think about the invisible microscopic battle that just took place to get it there? Thank you so much for joining me for this explainer, and keep asking questions about the amazing infrastructure hidden all around us.